right ahead.
Yeah, just close this. Okay, well. Well, thank everybody for coming. So this is my presentation for my bachelor thesis that I did in the last few months. And my bachelor thesis is titled Automatic Performance Optimization in DaCe using Deep Learning. I'm Benedikt Schesch, and I was advised by Professor Höfler and Dr. Benedikt. And as the title suggests, the main objective here is to use DaCe and combination of modern deep learning techniques that arrived to fully automatically optimize performance of a program. And for that, let's first take a look at DaCe and what it does, and then look at the old model of it, how nowadays it works. So nowadays we have a domain scientist who will write the code, which is usually inefficient, to solve like a given problem. And then he passes down to a performance engineer, and the performance engineer will rewrite the code, optimize performance, and usually apply some transformations among a relatively large set of transformations. And this is how it works nowadays. And DaCe noticed this and wants to change it a bit. And the basis of DaCe is to notice that the actual problem in modern computations is memory access and not the underlying computation. We see this in this diagram, that a memory access takes 1,000 times more energy than a simple computation. And so the data movement is really here the major bottleneck. And so DaCe creates this new way of this new paradigm in which we have still the domain scientist. He still writes this application. Here an example in Python, and he uses some simple DaCe constructs which are very easy, and you can also directly use NumPy to write this program. And DaCe automatically converts it to an SDFG, which is a new intermediate representation which DaCe has. And then the powerful thing about this representation that it's mainly about data flow. And we can automatically see performance enhancing transformations. We can automatically see them, and especially we can also automatically apply them, which is quite relevant here. And then we still have a performance engineer, since the domain scientists wouldn't really understand these transformations in our sense. And the role now of the performance engineer is now to pick and choose these transformations in an interactive process, such that it would reach a program which is optimal in performance. Here we have an example with the Laplace operator. And then the performance engineer would apply certain transformations in this operator until it reaches optimal performance. And so we want to look a bit more about DaCe before we go into this thesis, especially about this SDFG, since we will do all of our optimization based on this SDFG. So we want to learn, we want to use our machine learning techniques on top of this SDFG. So what exactly is this SDFG? Well, the SDFG is technically a stateful data flow graph. And so now we'll completely leave out the stateful part of it, since for simplicity, there's actually a data flow graph instead of states, instead of a state machine. So now we will only focus on one data flow graph. And what is the data flow graph? Well, it's a graph made out of these nodes. Basically, we have a data node, which just contains data, tasklet, which is a simple computational block, A plus B or something like this, addition, memlet, which represents the flow of data. And then all the concurrency is mainly showed by a map scope. Is the most important here. The map scope, we have the map entry node and the map exit node. And in the map scope, we have a parameter which iterates over a certain range. And it shows a parallel execution. And then we have write configurations that are similar to memlets, and then we have nested SDFGs, which are SDFGs which you can call directly from this data flow graph to abstract away other computations. And so we will only focus on these nodes. DaCe actually has more nodes than this, but we decided to, for simplicity, to only keep these nodes. These are more the most relevant ones, and we'll keep it like this. So as you've seen, the SDFG is a graph, and this is very important. And so first, before we start completely with the thesis, we want also to introduce you to graph neural networks. So what's a graph neural network? It's a way to learn on top of graph structured data. And graph structured data is basically anywhere in the world, financial transactions, anything, medical data. And so recently, in the rise of machine learning, there also was a strong rise of graph neural networks more recently, which starts to studies on top of graph structured data. And so typically what the graph neural network, the way a graph neural network's way works is by embedding the nodes into a common space and then learning the embeddings by having aggregations over this graph. And so what exactly is an aggregation? So an aggregation, here we take the usual case where to learn the embedding of the next layer, we aggregate the neighboring embeddings of the previous layer. And then we apply a certain aggregation function, which there's a large set of, and we'll see a couple of them, but they can be a little bit anything. And then here, for example, we start with layer 0, we do the aggregations for all the nodes, and we have all the embeddings for layer 1. We can do this multiple times to learn to spread information about the graph structured data more and more in the graph. And so what are the typical aggregation functions? Well, the first one is the max aggregation. It's the easiest one. We simply take the maximum of the neighboring embeddings, and that's the new value. Or we have the most common one, I would say, the graph convolution network, which is simply the average neighboring embedding, more or less the average neighboring embedding passed through a linear layer, which has learnable parameter, not like the max aggregation. And so now that we have seen SDFGs, we want to see more about the thesis itself. So we're going to give a bit of an overview. And this is here the new proposed model of the thesis, the new workflow that we propose. And as you see, we still have the domain scientist. It's very similar to DaCe, but we still have the domain scientist who will come and write a problem, try to solve a problem. And for that, he will use a program, usually a Python program, would be the easiest. And then DaCe still comes in and will create the SDFG through the API that they give. And once we have this SDFG, now we differentiate from DaCe. We want to propose this new workflow, which exactly no longer requires any performance engineer. And for that, we take the SDFG and we encode it into what we call an encoded SDFG, such that we can pass it to a graph neural network. And once it's encoded, we pass it exactly to the graph neural network model, and the graph neural network model should predict a certain transformation, which is optimal, such that it improves performance the most. And once it proposes this transformation, without doing any executions, of course, we give it to DaCe, and DaCe can automatically apply this transformation, and we output the transform SDFG, which gives us the program, which should be a lot faster and can be directly given to the domain scientist without any other intervention. And so this is the high-level overview of this thesis. And now we want to look a bit more on the first step, which is exactly the encoding of the SDFG. So the first problem, so here we have an SDFG, like a typical very small SDFG, but here we have one. And the first problem that will arise is that, for example, in a map entry, we have ranges. We also have in memlets, but we have a parameter which iterates over a range. And the thing is, for example, here the parameter I can be any string. It can be literally anything. And also for the range, here the symbol n can be also literally anything. And this would imply that we would need a vocabulary size which is enormous, which would support any string more or less. And so what we do is we do what we call symbol normalization, and we remap all these symbols to new symbols, which we normalize. And so, for example, the I would get remapped to I00, which indicates 0. The first one indicates we are in the 0th map entry, and the second 0 indicates that we are in the 0th parameter of that map entry. And all the remaining 3 symbols, which are not parameters, get reassigned to N0, N1, N2, N3, N4, etc. Once we have the symbol normalization, we can start to properly encode the graph and create node features and prepare the adjacency list that we will pass to the graph neural network. Since the graph neural network needs 2 things, adjacency list and the features for the nodes. And so how does the encoding work? Well, for most of the nodes, it's quite easy. Map exit, tasklet nested FG access node. We just do a one-hot type encoding to inform that which type our node is made of. And the remaining features are just set to 0. It's simply 0 padding, except for memlet and map entries, where we will fill them with a different vector. We will still have the one-hot type encoding, but we also encode them in a string of tokens. And so here we have an example of a map entry. The memlets, we won't cover it in the thesis. It's written in the paper version of the thesis. And how do we do this? We simply take the parameter of the map entry, we insert it, then a separated token, the beginning of the range of the range, separated token, the end of the range, separated token, stride of the range, and another separated. And the map entry can have multiple parameters with multiple ranges. And if we would have that case, we would simply append the same string, but we would all append them one after the other. We do something very, very similar on the memlets. And then we have encoded our nodes. Now we still need to create the graph that we want to use. And for that, we create what we call the graph encoding. And so here we take again the same SDFG that we had, and we have a different view of it, which is more of a network X view of the graph. And so we already have a couple of problems in this graph. If we would pass this to the graph neural network, we wouldn't take into account the information of the memlets, since our models don't take any edge features, they only take node features, and the memlets are exactly these edges. And so a common trick that one can use is to add a node, like here. So we add a node, the node number 6, which will take the features of the memlet, of the edge. And then we connect them to the source and the destination. We also add reverse edges everywhere, and we keep all the other nodes just as they are with the same features. We do this for the entire graph, and boom, we get all this. And we also do one other thing is we connect the map entry and the map exit nodes, since they create a so-called map scope, which is implicitly represented by these two map entry and map exit nodes, and we make it explicit by adding an edge and also the reverse edge. So now we have the graph, which is ready to pass. We have the features, which is ready to pass. So now we can start to use our model. And first, we want, as a soundness check, we want to verify that our encoding holds information, especially hold the semantic information of the graph. For that, we do what we call an encoding verification. We try a simple task on a memlet, which simply tries to see if a memlet accesses a one-dimensional contiguous array of data. And for that, we take just the encoding of the memlets with a string of tokens. We pass them through a learnable embedding layer. So we learn a vector for each token. And then we pass a GRU over all these embeddings, and we take the last hidden state of the GRU and pass them through a neural network to predict if or not it has a one-dimensional contiguous axis or not. So we train this network to see exactly if we are able to capture the semantics of the memlets. We have a data set of 432 memlets. This data set was created using the samples, the SDFGs built from the samples which are contained in DaCe. And we subsample the actual data set, since it's mostly a positive, since it's mostly the case, and the positive rate is very high, and we bring it down to 66.67%. We get the final validation. So we train our model, and we get the final validation accuracy of 100%, which shows that we're perfectly able to learn this function. And it also shows that we are able to capture the semantics. Our encoding is able to encode these informations, and modern machine learning techniques are able to use these informations to learn this function. So this is quite a success for our encoding. And now we want to move on and make some more complicated verifications. We still want to see if our encoding is useful, and especially we want to see if also we are able to learn information on the graph. And so we create a new task, which is about the vectorization transformation in DaCe. So what is vectorization of it? So vectorization is simply of doing one instruction for each element in an array. For example, here for the addition, we do a lot of additions at the same time concurrently. And for that, we use instructions which are called SIMD instructions, single instruction multiple data. And DaCe automatically can detect this transformation and apply it. And concretely in DaCe, what it will do, it will actually take a map scope and change it a bit such that the multiple iterations are executed concurrently. And so here we have an example of an SDFG of what it looks like in transformed one. We have a map scope, which iterates from 0 to 2048. And here we don't see the stride, so it means that the stride is 1. And then when we apply the vectorization, we get a stride of 4, which shows that we're actually doing 4 additions at the same time here. And so this usually results in good performance. And now what we want to do is we would like to see how DaCe works, is that it will match, it will see a subgraph of the graph, and it will consider it as a candidate vectorization point. And then it could be true that we could apply vectorization transfers, but it's not sure. A certain set of conditions need to be true such that we can do it. And we want to verify that we're able to learn these conditions, this set of conditions. And for that, we use our network. So we create this network, which is made, which is very similar to what we had before for the memlet part. So we still use an embedding layer, encode the string, we pass them for a GRU, and we do the same for map entry. We embed them, pass them for GRU, and then we have all the node features, all the node embeddings which are ready, and we can pass them through the graph neural network. And it's this, and then we take the adjacency list that we created and pass them through a max aggregation graph neural network that we implemented in PTGNN. And then we take the embedding of each tasklet, and we ask them to predict if that tasklet is vectorizable or not. We take a tasklet because we consider it as the anchor point of the vectorization transformation, since the subgraph that DaCe will detect is made out of a map entry, a map exit, and a tasklet. And the conditions, actually, the set of conditions are around the memlets, which are around the tasklet. So we take that node specifically. We take a new data, we take the same data set as before, but there we just take, we extract all the possible vectorization points. We get 1,202 data points and a roughly balanced data set. We try with the Adam optimizer and we get pretty bad performance. The accuracy is super stark, same for the loss. And we get the final validation accuracy of 58.8%, which is quite low. So what we do is instead, we try again with a different optimizer. Since an early experiment that we did on graph neural networks, we saw that the SGD optimizer would have a tendency to have a better convergence and converge for longer. We try again, same parameters, same everything, and we get a final testing accuracy of 95.3%. And so this is quite a good performance. The loss decreases in a normal manner, and we consider that we are able to learn the semantics of the SDFG quite well. And so now we consider that we can move on, and we want especially to see something which is more related to performance and to transformations, since this is the aim of the thesis. So for that, for performance and transformations, we will take a different transformation, which is called tiling. And this one simply takes a map and transforms it into two maps. One iterates over all the tiles, and one iterates inside the tile. And this sometimes can improve performance quite significantly, but the big parameter here is the tile size, what the actual size will be. And this one can have a super strong effect on the performance of these transformations. And so what we want to do in this new task is we want to predict if the tiling transformation will improve performance or not of our SDFG. We do that, and so here there's this parameter, the tile size, and we consider that it improved performance if for a certain set of tiling sizes it improves for any of them. Then we consider that it improves performance. If not, then we consider that it doesn't. This time we create a synthetic data set. We have here an example SDFG of the synthetic data set, and we have a positive rate of 33.3%, and the data set is made out of roughly 2,000 data points. And we do a performance measure over one execution. We use a network which is very similar to what we had with vectorization, which is mainly based on graph convolutions this time, and it uses DJL instead of PTGNN. Yeah, the main differences, the other ones are mostly similar. And we train our model and we get a validation accuracy of 78.48%, which is not very good considering that our data set is quite unbalanced. So this is not good news for us. And we create actually a manual classifier which tries to classify on heuristics if tiling improves or not performance. And the thing is, what we noticed quite quickly is that actually the performance itself was super unpredictable. And the root cause of this was that the measure is over one execution. And so we try again, we change the performance measure, and we now consider it as the median execution time across 10 executions. This helps a lot with our accuracy, and we managed to reach 93%, which shows that our model is definitely able to reason about performance and transformations. And the loss decreases a lot more too. And also, now if we take a step back, we would like to choose a transformation. This is important. Here we are only able to say if tiling might improve, if and only if we have a good tiling size, then we can say this. But we can't really say apply tiling here with this size, like the size is really missing here. And so we try a very similar task, but this time we want to predict the K, which results, so the tiling size, which results in the best possible performance. And so we create our data set with different tiling sizes, and we get the following, the number of data points in the classes. We see that the one class, so it's a class, it's a special class, since it means that here we actually don't apply any transformation. And we have a heavy data imbalance towards this class with 968 data points. And also the class with a tile size of 1024 is quite more prominent than the other classes. And so we use exactly the same network as before, but this time we have a multi-class classification problem, and we just simply predict we predict the probability for 6 different classes, and we train our network, and we get the following results. So we are still quite far from 100% accuracy, since we have 77.5 in validation accuracy, and most importantly, we get a speed up and a validation average speed up of around 16x, which is quite a bit under the 26x, which could be theoretically reachable under a perfect classifier. But it's still quite a significant speed up, I have to say. And so we would like to understand a bit what's going on. Why do we get this bad performance? It's not terrible, but it's not optimal. And so we look a bit at the confusion matrix, and we see that here, most importantly, for the no tiling class, we are able to predict it quite well. Our classifier is doing well. And for this 1024 class, our classifier is also doing quite well. But anything in between, we're super bad. We basically don't really predict anything. And so my best guess, and what seems to be true, is that the lack of samples in these classes, in these intermediate classes, prevents our classifier from learning properly. And this is the main thing that we notice. And so we would like to conclude a bit on all the work that we did. And most importantly, we proposed an encoding of the STFG, which captures the semantics of the STFG, and we show that we are able to learn information on top of it. And it's quite compatible with modern machine learning techniques. And we also show that in combination, the encoding in combination of graph neural networks, we are able to reason about the effects of transformations and performance. And most importantly, we managed technically to create, our goal is to create a model which chooses a transformation. And even though it is not optimal from a performance perspective, it still offers a significant speedup of 16x, which can be applied anywhere on any map entry. And there are usually multiple map entries for a graph. So it does for an STFG, so it does offer certain performance gains. Now, of course, this is just, we just want to show it as a proof of concept. And there's a lot of remaining work to do, especially to reach better performance, but also to create models which are able to choose among a far larger set of transformations to reach better performance, and also to be able to reason about chains of transformations, since you usually need to apply multiple transformations in a given sequence to reach optimal performance. So yes, and yeah, I would like to thank Dr. Ben Noon and Professor Höfler for having given me this opportunity to do this thesis. And if you have any questions, please go ahead.
Thank you so much. Now, any questions? Well, I have a few. Okay, so the first question is that in the encoding of the graph, you said you added some edges, some extra edges. Could you go back to that?
Yes, of course.
Yep, I think it's here.
Yep.
Yes, so there are a few extra things here. So every edge is bidirectional, right? It goes in both ways. Could you explain maybe?
Yes. So what we do is we add reverse edges. So we have an edge, and what we pass to the graph neural network is technically a directed graph. And so what we do is we add a reverse edge, such that information goes in both directions. This is usually quite important to have in a graph neural network.
Mm-hmm. And you said you added another set of edges between a map entry and the map exit. So exactly. Why did you add that? And what was the effect of that in terms of accuracy?
Well, the main goal, I mean, the main idea was here to come up with a good encoding, and we had some problems with accuracy on different experiments, especially if I remember here, it was about the vectorization experiment where we wouldn't reach good performance or good accuracy. And we tried a lot of different techniques to try to improve this accuracy. And one of them consisted of adding this edge between the two, such that information between the two can flow. And it didn't give a performance boost or something significant, but we decided to keep it since it does make sense. It makes implicit information explicit.
Mm-hmm. Thank you.
I have also a question. So first, I think this is great and interesting work. I really like the idea. One thing, especially when considering large SDFGs, so when we generate the SDFG, especially the way I do it with migrating them out of other procedural codes, the initial SDFG is huge and not necessarily optimized. So there's a lot of strict transformations that we can do. And we've seen that the order in which we apply transformations can have a significant impact on performance and on the resulting SDFG, because, of course, depending on the order in which you apply transformations, you can get different results, and you can end up in local minima, so to speak, where you, because of the fact that you apply transformation A, you can't apply transformation B anymore.
Yeah, exactly.
Do you think your approach could be extended or used for this kind of thing as well?
I hope. I mean, I think yes. I hope yes. The thing is, so the main step here would be to change from predicting one transformation to sequence of predictions. And if you think about it, it does come quite well with what we call reinforcement learning, where we would try to predict the next action, and we try to predict the next action, a sequence of actions, and then we give a certain reward. And if we could fit a reinforcement learning model on this, we can see that the tasks are quite similar to a typical reinforcement learning task.
I agree. What I'm wondering now is whether the reinforcement learning would be general enough, or it would just learn to optimize one graph. So the thing is that if you look at, for example, I don't know what examples you had in your testing, but if you compare something like a polybench example, one of the small ones, to something like Omen or a Stencil or Lulesh, so that there's the SDFGs themselves, because they represent computer programs, can be very varied, and I can imagine that there might be common patterns of optimality, but I'm not sure if there is always the correct order of transformations. I'm not sure. I'm really leaning out the window on this one.
Yeah, no, it's a good question, and I think this would probably depend on how diverse their underlying data set is, which was actually a big problem we had a bit in this thesis, is that you have to create automatically data sets. We had synthetic data sets. They will, of course, be quite heavily biased towards certain types of SDFGs. And yeah, it would be maybe a good idea to find a way to create SDFGs which can be very diverse.
Did you did you use in your evaluation some of the SDFGs which are already available, which aren't synthetic and are made from real applications? So like the ones from NP Bench or the ones from C2DaCe?
No, we actually, this would have been good to actually add this, but no, we didn't evaluate the data set. We actually only evaluate on the synthetic data set itself, and not on the real data sets.
So I agree that we don't have, Tal, correct me on this, I don't think we have like hundreds of thousands of SDFGs, but I think we're over 1,000 by now.
Yeah, definitely. I think we're around 1.5 or 1.6K when I had them. But yeah, it would be a good benchmark to try them out.
It's definitely a good test set, right? If you
exactly
train and validate on synthetic graphs. I actually had a question about another side of this, about the diversity of transformations. So can you tell us what you used vectorization and tiling, right? So what ties you to tiling? Is there anything special about your code that relates to tiling, or could you just apply this on any transformation now? Your code.
So I'm not sure about the question exactly.
I want to learn not tiling. I want to learn the effect of map fusion. Okay, if it's useful for me to do map fusion, yes or no? Right, it's another transformation.
Well,
it follows the same kind of interface, right? It's just a transformation. But now I'm asking, what stops me from doing this? Like, is your code specialized to tiling in any way?
No, so exactly. The code is not. This is actually, we actually did this when we tried to detect the vectorization. We made the code such that it's not specialized. You just could input any transformation and then try out the model on the given transformation to see if it could predict it well or not. And then for the performance prediction, it's not really specific for the tiling transformation. The only thing that you need to make sure of is that the transformation has a certain anchor point, so a certain node which we use for the classification. The node needs to make sense so that we have at least a hope of being good at the prediction. But otherwise, it's not specific to a certain node. We can simply replace a couple of lines with the given transformation and replace the anchor point, and you have exactly this. You have the same classifier for a different transformation.
Very nice. Now, another question, I guess it will be the last, unless Lex, do you have any other questions?
No.
Okay.
But I think this is great work, and I think this would be a great thesis to continue and pursue. So expand on it.
I would have liked to continue, but time has been a bit short.
Yes, last question then about graphs. So Lex here mentioned before that some of our graphs are really large. And so if you want to apply this automatically, how would you deal with such graphs? Like here, your graphs only have one map, so it's possibly like easy to tile and test the performance. How do I test your system on a full application graph?
Well, this is a bit of a problem because like the SDFGs that we generated are not that large. Like they are not very, very large. And therefore, we had the example SDFG that I showed here. And so how could the scale to larger graphs? It would probably be by either already increasing the number of layers that we have of the graph neural network, which means that we aggregate more information about the neighbors, about the structure of the graph and all the neighbors. The more layers we have, the deeper we can go into the graph. Another method, which would be a bit different, would be to bring together all the possible transformation points, and then create a model which predicts on top of these points that tries to choose one point, which is the optimal point. They had this a lot when these are called pointer networks, if my memory is well. And they had this a lot in, for example, if you look at the paper about StarCraft that DeepMind made, they had networks which exactly, even though we had a huge set of actions, so a huge set of possibilities, they would have a network which would come down and exactly pick one. And these networks which would exactly look at the embeddings of all these actions.
Sounds good. Sounds, yeah, like two good ideas. And the other one is, of course, just do it on every map separately, right? You could also try that. Maybe if it works, it works.
Yeah, I mean, for the tiling transformation, they are relatively good. I mean, except if they are nested, they should be quite independent between for the performance.
Actually, how does it work with the anchor? How do you tell the graph neural network to focus on a specific map?
Well, for the map, so for the time transformation, the anchor point we consider it as the map entry of that. Yes. We got split into two map entries. So, for example, here it would be this map entry. We would take the embedding of this map entry, which would pass for a dense neural network, and then we focus on exactly on this tiling.
Yes, but the input to the graph neural network is a whole graph. So how do you let the graph neural network focus on that specific map entry?
Yeah. The input is a whole graph, and the output are embeddings for each node. And we pass the embedding of the anchor point, so here only of the map entry, and we pass only this embedding through a dense neural network.
I see. Okay. So you take the whole graph and then you filter out the ones that you're interested in.
Exactly.
So yeah, then a pointer network might work as well.
It's not super efficient since we're learning all the embeddings at the same time. There could be some performance improvement on this, but yeah.
Okay, thank you.
Yep, thank you.
Okay, I'm going to stop the recording now.